right, let's take a look at this buffer question. And I've also packed in polyprotics, and I've packed in a salt in there too, or two salts. So this has got a lot of concepts sneakily hidden in it. So let's start off with, what are we making? I'm asking for the pH of a 1 liter buffer. So I've already told you that I'm preparing a buffer. Hopefully I do it right. And I'm making it from these two salts. Okay, so my first step is I want to know what are the ions that go into solution when those salts dissolve. So let's look at this first one. So Na2HPO4. That's going to dissolve and split up into two Na pluses and HPO4 2 minus. Okay, I am more concerned with that HPO4 2 minus. Na plus is an unreactive cation. It's a spectator. It's not densely charged enough to draw in waters and create some acid. It's just there hanging out. Okay, so that's one thing that we've put in that we need to take note of. And then we also put in NaH2PO4. That splits up into one Na plus and H2PO4 minus. Okay, so these are the two species that I'm interested in. And I want to know how they're related to each other. So if I look at the second one that I put in, that has one extra proton. Okay? So if I lost a proton from that H2PO4 minus, it makes the HPO4 2 minus. In other words, this is the acid, and this is its conjugate base. I want to make that distinction because if I'm going to do a pH calculation on a buffer, I'm probably using the Henderson-Hasselbalch, which we talked about on Tuesday. That's pH equals pKa plus the log of the base over the acid. Okay, and so these are the concentrations. Okay, so I need to know which one should I call the acid and which one I should call the base. So this one, even though it is already negatively charged, that's my acid because I'm adding in its conjugate base. So now I can identify those and put the right numbers into that parentheses, into that fraction there. The last thing I need to do is pick the right pKa. Okay, so I've already established that this is the thing in my solution that's like the acid, right? That has the extra proton on it. Okay? And I look at, I've given you 3 pKa's for H3PO4. You're going to bypass that first one because I didn't put in H3PO4. That pKa of 2, that's talking about the release of the first proton. But I never put that in there. I never put H3PO4 in. That acid that I put in was the H2PO4. So I'm thinking about the removal of that second proton. So H2PO4 minus, dissociating into H plus, and HPO4 2 minus. So I want to know about this proton, and that's Ka2, so I want to pull the pKa for that proton coming off, the second deprotonization. So I'm going to have pH equals 7.20 plus the log, and I just want to make sure I don't screw up grabbing the right numbers. This 0.78 was for my conjugate base, so that goes in the top. And the 0.94 was for my H2PO4 minus. So I got a pH of 7.12. Okay, so lots of little pieces from the last couple lectures stuck into this problem. Questions? Yeah. So the pK, if I had made a buffer with H3PO4 and NaH2PO4, let's say, then I would have been dealing with these two species. And I would have looked at this and said, that's my acid. This is its conjugate base. I should pull the pKa for that acid. That's pKa1. So that would have put me at 2.15 for my pKa. But I didn't start with those two species. I started with H2PO4 minus and HPO42 minus. And I look at the relationship between them and say, this is my acid. It's giving up a proton to make its conjugate base. I should pull the pKa for that thing, for that H2PO4 minus. And that's the second pKa. Yes, I'm going to think about it through the lens of the acid because our Henderson-Hasselbalch is set up as the pKa. So I want the pKa, which is describing the acid. All right. Let's do another jog your memory. So this time, this is a simpler buffer in that it's not something that had a polyprotic. But now I'm gonna push you a little bit further and say, hey, I've got a buffer, and now I add some strong acid. Can you calculate the pH after I've added some acid to it? Okay. So as a reminder, just to get you started, these are the questions you should start with a BCA table and then do a Henderson-Hasselbalch. Okay, so try and set that up for yourself. All right, let's take a look together. Let's remind ourselves, I'm going to backtrack just a touch and say, what is a buffer? Okay, our buffer is something, our goal is to stop pH change. Okay, so a buffer resists pH changes, even when you add in a strong acid or a strong base. Okay, so we have a buffer. Again, I've told you it's a buffer in the question, but you could have identified it as a buffer because you see this weak acid, so formic acid, and we've added in sodium formate. So remember that language piece or the nomenclature piece, ic acid is the carboxylic acid of the weak acid, so it's looks like this. We'll draw this properly. Okay, so that's formic acid. So that is my acidic proton right there. But then I'm also adding in sodium formate, which looks like this. It has that H pulled off, and it's a salt. It's partnered with Na+, which again doesn't have an impact on my solution. It's a spectator ion. It just hangs out, and it's happy to do so. All right, so I've got those two things in there. That makes a buffer, because if I add in some strong base, my formic acid will neutralize it, right? If I add in some strong acid like we're doing in this, my formate my weak base will neutralize that. So you have something of each, you have a weak acid and a weak base, and they can neutralize and stop the pH from changing all that much. Okay, so in these questions, sort of practically speaking, when you have a buffer and you're adding in something, you start with a BCA table. Okay, so this is done sort of the stoichiometry approach, and it's in moles. And let's talk about the chemistry. We have H+, that's what we're adding in HCl. It's a strong acid. Really, I'm just putting in H+. Cl- doesn't react in the same way that Na+ is a spectator ion. Chloride is just happy to hang out, doesn't get involved. So I'm going to have H+ in solution. Okay? It will react with my weak base to make, so 100%, we're not thinking about this as an equilibrium. If I put in strong acid, I'm going to convert my weak base to the weak acid, 100%. Okay, so that's why we're not really thinking about this as an equilibrium. It's not a balance. I'm just saying 100% of that reacts. So I need to know the moles to put into this table. All right, so how many moles of HCl, of H+, did we actually add? Okay, so that's going to be 0.005 liters. I'm just converting my mils to liters. And it's a fairly strong concentration at 10 molar, so I'm adding in 0.05 moles of H+. So that's my before value here. I made this easy for us. I have 0.75 moles of formic acid and 0.75 of the formate. Those are just equal to begin with. Okay, so H+ is my limiting reactant. That's the smallest number in my before row, so I'm going to use that. I'm going to subtract it from the left side and add it to my right side. Okay, so we've neutralized all of that H+. We've had to use some of our formate, some of that HCOO-, so we wind up with 0.70, and we gain that in our HCOOH. So it's sort of big picture, I put in a strong acid, and instead of just increasing the concentration of H+, I've actually just increased my HCOOH a little bit. So instead of adding a strong acid, I've added just a little bit more of my weak acid. So that's why I'm not seeing a huge pH change. These are now the values that I can take and plug into a Henderson-Hasselbalch. Okay, I have a large amount of my acid and its conjugate base. That looks like a Henderson-Hasselbalch problem. So pH equals pKa. I need to take the negative log of that to get my pKa. That's 3.74. Plus the log of my new base concentration, or moles. So I can do this calculation in moles because my acid and base are sitting in the same volume, right? They're in the same container, so my volume is the same. So moles over moles is going to be equal to molarity over molarity. If you want to convert to molarity, that's fine. I just like skipping that step because I don't have to do it. And I wind up getting a pH of 3.69. Okay? So even though I added in 5 mils of a really strong acidic solution, my pH is only changed by 0.05. Okay? That's the effect of the buffer there. It doesn't let the pH change very much. It resists that change. Okay? Questions on that? Okay. This is a really good jumping off place for us for what we're going to do for the rest of class, which is titrations. So it has a very similar, the structure of this problem is very similar to what we're going to do for the rest of class. So in that, we will do some BCA tables and then do a follow-up calculation. All right. So let's do it. Let's talk about titrations. Just by show of hands, who's done an acid-base titration in lab before? Hey, we've all done them. Have you done them already in this lab? No? Okay. So procedure in which one reactant is slowly added to a solution of another reactant. All right, so we have, in this case, this is showing us an acid solution we added an indicator. Remember that we were going to talk about the chemistry of indicators at the end of lecture. Okay, but something that's going to change color at a certain pH. Okay, usually this is unknown concentration. And this is known. We're going to start titrating. We're adding in a known concentration of something else. And we can then say something at the end of this, once we hit our equivalence point or where we see that color change, depending on how much we added in, we can say now we know the concentration of what was in our original beaker, okay, or Erlenmeyer, as this picture shows. So that's usually the reason why titrations are done, to determine the concentration of one of the reactants. We'll find that we can also determine the equilibrium constant for the reaction. In this case, we can find what the pKa of our acid is. All right, so all of this hinges on our ability to find and interpret this equivalence point. Okay, so that's our next slide. We want to know, when do we hit the EP, or the equivalence point? Okay, so let's talk about what the equivalence point is. All right, so that is when our moles of acid equal our moles of base. Okay, they are stoichiometrically equivalent. So let's say I have, we'll do an Erlenmeyer to make it consistent with our previous picture. Okay, so in here I have some H+, but I don't know what the concentration is. Okay, so I'm going to add in OH-, and I know how much OH- I'm adding in until I see that it's equal. Okay, so I'm adding OH-. The equivalence point is when I've added in the exact amount, and they're all matched up. If it was a strong acid, strong base, now I have neutralized all the H+ with OH-. I've just made water, and this thing should be neutral. It should be at a pH of 7. Okay? But with like that visual of like you're adding it in, you're waiting for when those two things are equal. Okay? There's a couple different ways for us to identify that point. Okay? So when we're looking at a titration curve, which we'll do a lot of today, we're looking for the vertical asymptote. So we're adding in our OH-. We're tracking pH, and our curve is going to wind up looking like this. There's going to be a really big rise. So this is what we call the rapid rise portion of the graph. At the middle there, in the middle of that rise, that is our equivalence point. Okay, when all of a sudden we're going, it's acidic, it's acidic, it's acidic, and then boom, we switch over, and now it's basic. We went through that point where we had equal amounts of H+ and OH-. That's the equivalence point. And if I give you a graph like this, you can identify the mils that I needed to add to get to that EP, or the pH at that equivalence point. Okay? The other thing we might do, as I mentioned on the other side, or on the other slide, was we put in that acid-base indicator, something that changes color at that EP. Okay? That can also be a signal. So we'll look at that in more detail, but we might have something that is green at the equivalence point, and it's blue after it. And this probably isn't landing right now, but when we look at this later, we're going to say, oh, before we hit that equivalence point, it's yellow. At the equivalence point, it's green. And then if we go beyond it, it's blue. So we have some other chemical in there that's giving us an indicator of the pH. Okay. Yeah. Yes. Yes. No, I'm not going to talk about this anymore. I'm just kidding, we're going to do examples now. We have 4 different titrations, and and I'm going to split them up based on whether or not we're dealing with a strong acid and strong base, or if one of the components is weak, because that is going to differentiate the calculations that you do. So we're going to start with the easier of the two, where we have a strong acid titrated by a strong base, or vice versa. This is simpler, let me say, because we are just dealing with a neutralization reaction between H plus and OH minus. So we're just making water. And that water, that product that we're making, isn't going to have an impact on the pH. It's just going to be, hey, once we hit that equivalence point, the pH is 7, because we've neutralized all of our H plus with OH minus, or vice versa. Okay, this is not going to be true when we deal with a weak acid or a weak base in our titrations. So in our weak acids, we're going to titrate with OH minus. And in doing so, we wind up making a bunch of A minus, the conjugate base. And that's going to have an impact on our pH. So we have to be aware that we're making a weak base as we titrate. The reverse is true for a weak base, where now I'm titrating with H plus, and all the while, by doing that, I am making BH plus, which is a weak acid, and I have to have that in mind. So that's why these two types of titrations are different. When it's strong, we're just making water, and we don't have to think about that, because it's just going to be a pH of 7. But in these weak acid, weak base titrations, I am making something that is then going to have an impact on my pH, and I have to be aware of it. We're going to start off with these two simpler strong acid, strong base titrations first. All right. So here's our titration curve. Here's it actually written out from the book. This is really similar to what we drew before. We're adding in mils of NaOH. We're tracking the pH. We see this huge rapid rise here, and our equivalence point is right at the middle of that, and in this case, it's 7. And again, that's because we're neutralizing H plus with OH minus. So at that equivalence point, I have just made 100% water. In this case, I would have Na plus and Cl minus floating around, but we know those are unreactive cations and anions, so I just have a salty pH 7 solution. Okay? So this is the main chemistry that's going on in these strong acid, strong base titrations. So let's try it with numbers. So we're gonna do out this titration. So the unfortunate part about titrations is that you have to do a bunch of calculations, because we're going to start when we don't add in any, then we'll add in a little bit, and then a little bit more, and a little bit more, and more, and more, and we have to do the calculations at each one of those points. So that's why titrations can feel onerous, because you have to do a bunch of calculations. So we're going to start off with just 0 mils. I haven't added in anything. I'm asking myself, what's the pH there at the starting point? Okay? For 1 liters of 0.15 molar HCl. So this is something from the last exam. I want you to do that for yourself. What is the pH of that solution? It's 0.15 molar HCl, and I haven't added any NaOH. What is the concentration of H plus in that solution? Turn to someone next to you. Give me a thumbs up if you knew how to do this, or if you feel like you knew how to do it. Is HCl a strong acid? Yes. What does that mean? It 100% dissociates. That means I have 100% H plus and Cl minus. Again, that's a spectator, doesn't do anything. I have 0.15 molar of H plus. That is what I then plug into my pH equation. pH is the negative log of that concentration. So to start with, I have a very low pH of 0.82. That is our starting place, okay? But now I'm going to start adding in some NaOH, okay? So that's what we're going to do on the next slide. Now we are into our titration, okay? Now we're here on the titration curve. We're at that 25 mils, okay? And I want to know the pH when I add in that 25 mils. So I need to do a BCA table. I need moles. I need to know how much H plus am I going to neutralize. Okay, so I'm thinking about H plus OH minus goes to H2O before, change after. So I have H plus. I've got 1 liter of 0.15 molar. So I have 0.15 moles of H plus. For OH minus, I'm adding in 25 mils, which is 0.025 liters, times 3 molar. And that's 0.075 moles. So those are my initial concentrations. That's before the reaction has taken place. So I'm going to put that in my B row there. 0.15, 0.075. And I don't care how much water we have. All of this is taking place in water. There's a bunch of it. Okay? Notice that OH minus is my limiting reactant. I have not neutralized all of the H plus. On the curve, that means I am before the rapid rise. I haven't reached my equivalence point yet. That's somewhere in this region. Okay? I haven't added enough to consume all of my H plus yet. Okay, so I'm going to use that. I'm going to subtract 0.075. And again, I'm adding that in water, but I don't really care about it. That leaves me with 0.075 H plus. Okay, and then you remind yourself that you are in moles and that you do need to go back to molarity. This is one of my most common spots to make a mistake. So don't do it yourself. So that's my moles of H plus. I want to take it to molarity. So I have 0.075 moles of H plus. And now my total volume is 1 liter plus 25 mils, because I added in 25 mils of my NaOH solution. So my total volume is 1.025. That's 0.073 molar H plus, and now I can just take the negative log of that. And that's 1.14. So that's our next pH in our table. Mm-hmm. I'm adding, we had 1 liter of our solution. So imagine this is our like Erlenmeyer. It had 1 liter in it, and then I've added through my like burette, I've added in 25 more mils. So my total volume, this level is increasing as I titrate. And we have to take that extra volume into account when we calculate the concentration. Okay. All right, so that's 25 mils. Now we are going to do 50 mils. And on our graph, it's already given away. This is where our equivalence point is. Okay, there's 50, so we're right here. But let's check it for ourselves and identify it as our equivalence point. So again, I'm just going to pull the moles of H plus from our previous slide. Nothing has changed about that. I still have 1 liter of 0.15 molar HCl. So I have 1.15 moles of H plus. But now for my OH minus, I'm adding in 50 instead of 25. So I'm adding in the exact same number of moles of OH minus. In other words, every single H plus in solution has now been neutralized by an OH minus. We can write it in our, like it's good practice to do this in a BCA table because it's going to get more complicated when we're dealing with a weak acid and weak base, so we might as well give ourselves the best habits. So they're equally matched. And I wind up with 0 of both. Okay? So that means in this solution, I only have H2O. And remember, H2O has its own equilibrium because it can auto-ionize. It can sort of act as a base and as an acid. So it's constantly breaking apart into H plus and OH minus. And that equilibrium is described by Kw, which is H plus times OH minus. We know that at room temperature, that's 10 to the negative 14th. Okay? At this point, I don't have anything changing H plus and OH minus. Those should be equal. In other words, each one of those concentrations is 10 to the negative 7th. So the pH of the negative log of 10 to the minus 7th is just 7. We have neutral water here. Okay, so at the equivalence point of any strong base, strong acid titration, the equivalence point is always has a pH of 7 because we're just making water. So when we have completely neutralized our OH minus and H plus, that means we have a pH of 7. Okay, so that was this point on our curve. Now let's go beyond it. What happens when we blow past our equivalence point? And now we are just adding in excess OH minus. So you see that pH continuing to spike, right? It goes way past 7. We are now up here. We are adding in OH minus, and there's no H plus left to neutralize it. All right, so let's do that again. We're now at 55 mils. We're still working with an H plus moles of that 0.15 of our original 1 liter of HCl. Okay, but now we're adding in 0.055 liters of 3 molar, and that's 0.165 moles of OH minus. So those are the numbers I'm going to now take and put in my CA table. And I see that I'm beyond it. My limiting reactant isn't OH minus anymore, it's H plus. Okay, so I've got 0.15 here, 0.165 here, and I look at that and I say, oh, this is my limiting reactant. So now I'm going to subtract 0.15, which leaves me with 0.015 moles of OH minus. Okay, and again, that's moles, and you've got to bring it back to molarity. So this is moles of OH minus. We want to bring it to molarity. So that's going to be 0.015 divided by our new total volume, which is 1.055. Okay, so I've got a concentration of 0.014 molar. And that is OH minus. So if I take the negative log of that, that's my POH. And we're usually going to be asking for pH. So make sure you don't make that mistake. So we could take the negative log of 0.014. That's my POH. That equals 1.85. And to get pH, I'm going to take 14 minus that number. And that's 12.15. Okay, so you will undoubtedly see some of these questions on the exam. And I think that just, if you see a titration question, start by going into moles, do a BCA table, ask yourself, where are you? Are you before the equivalence point? Are you at the equivalence point? Are you at it, or are you after it? Get your mind, like, think about this graphic and where you are on this curve. Are you here, here, or here? Here, technically, we haven't started a titration yet, but that's the last place, that's the last region that I spread out in this. All right, so there's our final, we did this, we went through and we plotted that out. This was purely driven by calculation. We already knew what our concentration of the strong acid was, so like lab-wise, in terms of like why would one do this? This is really just to like make sure you can do the calculations. A more meaningful question comes, we're going to come back to this one. I want you to answer this question first. What is the concentration of a 100 mil HClO4 solution if 7.9 mils of 11.4 molar potassium hydroxide were needed to reach the equivalence point? Okay, this is so like now we actually had an unknown. Now we're trying to figure out what was in that beaker. What was that 100 mils of HClO4? What was in there? And we did it, apparently, we figured it out using a titration. All right, what do we know about the equivalence point? Okay, by definition, if we go back to our equivalence point slide, that was when we had equal amounts of H plus and OH minus. Okay, in the question I just gave you, we don't know this value. We don't know how much H plus was in there, but we know what the OH minus was, and we know they have to be equal because I've told you we're at the equivalence point. Okay, so once I know that 7.9 mils of this very concentrated potassium hydroxide were needed, now I know the moles of OH minus, which tells me the moles of H plus. Because remember, HClO4 is a strong acid. So I'm going to take 0.0079 liters, so a very small amount, 11.4 molar. This is my OH minus moles that I'm calculating out here. And that equaled 0.0901. That at the equivalence point also needs to be equal to the moles of H plus, right? That must have been how many H plus ions I had in that 100 mils. So my last step is to say, well, my concentration of HClO4 was 0.0900 moles of H plus, and it was in 0.1 liters, right? Because it was in that 100 mils to begin with. Okay, so I want to know the original concentration, not after I've added in my 7.9 mils. And that is 0.9 molar, or if we want to be more precise. 0.901 molar of HClO4. And what was the pH, in your mind, answer, what's the pH now of this solution after adding the KOH? Gotta have a pH of 7, because all of our H plus has been converted to water with the addition of OH minus. Okay, so this is like the more meaningful way of orienting these questions, because it's the other way it was like, okay, well, we know the concentrations of both and now we're calculating pH. Here we're saying, well, we don't know what the concentration of one was. Why, like this gives more justification to why one might do a titration. Okay, we could back calculate what the concentration of this unknown solution was. All right, now we're gonna go back a slide. I wanna go back to this one. The strong base, strong acid titration, where we're starting with strong base. So the strong acid in this case is our titrant, the thing in the burette. Okay, so we're starting now, it's like almost the mirror image of the graphs we have been looking at. We're starting at a very high pH, it's very basic. Okay, and then we're adding in HCl, we're neutralizing. So we have lots of OH minus here. We're slowly adding in H plus, neutralizing. All of a sudden, we completely neutralize it at our equivalence point, again, which has to be at 7. And then we shoot past it, and now we just have a really acidic solution down here, past that equivalence point, because we're just dumping in excess H plus. Okay? So it is off, like there are homework questions. One of my post-lecture questions has you analyze the graphs. So these are, it's worth knowing and being comfortable with these figures. All right. So that was strong base, strong acid. So our first two types of titrations. And now we're going to hit our weak acid, strong base titration. Okay, so this was the harder of the two flavors when we split them out. Okay, so we're going to look at this in 4 regions. Okay, and they're the same regions we looked at before, but we're going to have unique types of calculations for each one. Okay, so we're starting with 250 mils of a 0.5 molar solution of acetic acid, so a weak acid. All right. And we're going to add in some NaOH. Okay? We're going to split this into 4 regions. So here's our first region, and then we're going to calculate here at the equivalence point and then beyond. All right, we're going to do calculations at each one of these points. And we're going to use separate approaches for each one. Okay, they're not all that different, but I think it helps to organize it this way. So for this first point, where the titration hasn't started yet, we are just doing a weak acid calculation that we've done many times before. It's an ice table with our acetic acid. All right, so we'll do that on this page here. We've got CH3, COOH, it's a weak acid, so a small portion of it, a small percent dissociates into H plus, and its conjugate base, the acetate ion. Okay. We could do this as an ice table. We're starting with 0.5 molar and none of the products. We lose a little bit, gain a little bit of our products. We use our 5% rule and say that X is probably pretty small, so we can assume our equilibrium concentration of acid is basically the initial concentration. And we wind up pretty quickly with this expression, which I wrote up here. That's the place you can jump to if you feel comfortable with these calculations. And it equals 1.8 times 10 to the negative 5th. That's our Ka for our weak acid. You solve out for X, which gives us 0.003 molar. That is our H plus concentration. Plug that in to get a pH of 2.52. Okay? This is why it was important not to ignore exam 2 content, because it is just, it's like your shadow. It's following you. Okay? So that's our first point. And now things get more interesting, more complicated, as we start adding in some mils of our NaOH solution. Okay? So let's think about that. We are going to put in 20 mils of our NaOH. This is before the equivalence point. So I've circled the region where we are. Our moles of weak acid is greater than our moles of strong base. Okay? So we are going to then convert some of the weak acid into its conjugate base. And we will have meaningful concentrations of both. And that is a buffer. So we've essentially made a buffer in this portion of the titration curve. And you all have already done buffer calculations. So this is nothing new. It is just recognizing that this is a buffer. All right, so let's do this calculation. We're going to start. Here's my steps. We're going to calculate the moles of HA and OH minus. Okay, so CH3, COOH, that's what I'm calling my HA. Okay, we've got 250 mils, or 0.25 liters, of 0.5 molar. Okay, so in this solution, we have 0.125 moles of HA. And now I'm going to add in 20 mils of sodium hydroxide. And the thing that I really care about is that OH minus that I'm adding in. So 0.020 liters times 2.5 molar. And that was 0.05 molar. Sorry, 0.05 moles. Okay, so now I've done step 1. I'm going to put that into a BCA table. Okay? I know that CH3, COOH, when I add in OH minus, a strong base, 100% of the time, we're going to think about it grabbing that H and making CH3, COO minus, and of course some water, but we don't care about the water. Okay, so we've got 0.125, 0.05, and 0. Notice that our OH minus is the limiting reactant, so I'm going to subtract that. We consume all of it. And in that process, we're making our conjugate base. So I'm going to have 0.075 of my CH3, COOH. We've consumed all of the OH minus, and I have 0.05 of the conjugate base. Okay, of the CH3, COO minus. And this is the point. You realize, hey, we are before the EP. We're not at the equivalence point yet. I haven't consumed all of my acid. I've neutralized my OH minus. I've made some of the conjugate base. And so this is a buffer. This is one of the ways we talked about making a buffer. Just start with the weak acid, add in a little bit of strong base, you make a buffer. So I'm going to take these numbers and put them into a Henderson-Hasselbalch. Okay? So pH is going to equal, the pKa from this is 4.74. The negative log of 1.8 times 10 to the negative fifth is 4.74. That's what goes here. And we'll write this just for good practice. This is the Henderson-Hasselbalch. I get the pKa by taking the negative log of the Ka. And now I have these values, 0.05 divided by 0.075. Again, I can leave it in moles because I just have moles over moles. Okay, that would be the same as molarity over molarity, because of course the volume is the same for both. The pH at this point is 4.56. Yeah. No, this is the HH, the Henderson-Hasselbalch, only when you have meaningful amounts of the acid and the conjugate base. The Henderson-Hasselbalch is for buffers, which means that you have to have a lot of the acid and a lot of the conjugate base. We have found ourselves in that position here because I have meaningful amounts of CH3COOH and CH3COO minus. That's my acid conjugate base pair. Well, I mean, if you take the concentration of it, it's a lot more than anything else in the solution. It's meaningful. All right. The thing I'll point out to you as well is that notice as we're adding, this is our buffer region, as we're adding in our NaOH, the pH is not changing very much, right? So we go from 10 to 40 and our pH only raises by 2 units. Compare that to going from 40 to 60, and we have that enormous jump. So you see that the pH, like we're resisting change to pH in this region. That's what tells me it's a buffer. It's not changing pH very rapidly, even though we're dumping in NaOH. All right, that was the previous slide. Now we're moving forward, and we're going to be at the equivalence point. Okay, and so this is why this is so different than our strong acid, strong base. Because at the equivalence point, our moles of weak acid equal our moles of strong base. Okay, so I have HA plus OH minus, and they're perfectly matched, and they 100%, approximately 100%, make A minus. So now in solution at the equivalence point, I don't have just water, I have a concentration of A minus, a weak base. So this is going to be basic. It's not at pH 7 anymore. Characteristically, the equivalence point is always greater than a pH of 7 for a weak acid, strong base titration. So always pH greater than 7 for this type of titration. Because we didn't make water, we are just sitting here generating a bunch of conjugate base, and therefore it's going to be basic. Okay, we made a bunch of A minus. That A minus is a weak base. We should see that in the pH. Together. Okay, now at 50 mils, again, it's the same process where we calculate our moles, put it into a BCA table, but this time we're going to see that the moles are equal. And you'll be like, I'm at the equivalence point. Okay, so let's do that for ourselves here. So our moles of acetic acid hasn't changed. It's still 250 mils of 0.5 molar. So that was our 0.125. Our OH minus moles now is the 0.050 liters, or our 50 mils times 2.5 molar. That also gives us 0.125 moles. Okay, so at this point in our BCA table, we're going to convert all of our acetic acid into the acetate ion. So again, now there is like real meaning to this step, because you remind yourself that, oh, I am making a bunch of this acetate anion. What should I do with it? Okay, so I think about this as like the, I don't know why this is popping into my head, but you know when you use like sandpaper and you sand it the first time, and then you have to like go down and you use like a finer grit. So like this first step is just getting us like the rough estimate, and then we have to do the fine tuning with our fine grit sandpaper. So I'm going to say, hey, now I have, actually let's do this down here. We're going to take this is moles of CH3COO minus. I need it in molarity, because now what we're going to do is a weak base calculation, just like we did in chapter 16. So again, something else you have done before. Okay, so 1.125 moles divided by 0.3 liters, because I am now taking into account that my volume is getting bigger. So I'm adding those two together. And I have a concentration of 0.417 molar. Okay, so again, I've made a weak base solution. And what do weak bases do? Well, they make a little bit of OH minus. So now I say, hey, I'm going to take that and put it into an ice table. This is the most onerous of our titration points, okay? Because we have to do a BCA table and an ice table. All right, I'm saying we've converted everything is this CH3COO minus. But I know that's not true. A little bit of it actually does make that OH minus. So now I'm going to use my equilibrium to assess that. So minus X, and I'm going to use my 5% assumption. This is why I said that this first step was a real rough estimate, that 100% of it makes that CH3COO minus. But then I say, well, yeah, I did make all of that, but I know some of it is going to dissociate. I know that it has a KB value that has meaning. So now I have to do that calculation. So I grab these equilibrium values. And I'm going to move up here where I have a little bit more space. KB equals x squared over 0.417. And I used KB, right? Because I made the weak base. So I need a base dissociation constant. We didn't get a KB. Can we solve for the KB? Yes, because we have the Ka of its conjugate acid. So I'm going to say that this is equal to Kw over Ka, which is 10 to the negative 14th, divided by my 1.8 times 10 to the negative 5th. Okay, that equals 5.6 times 10 to the negative 10th. Now I can solve for x, because I know x squared over 0.417 equals that 5.6 times 10 to the negative 10th. And so x, which is our OH minus concentration, equals 1.52 times 10 to the negative 5th. And then I convert that to pH, and I get 9.18. So this is obviously a many-step problem, but I'd argue that all of the steps you've already done before, right? We've got a BCA table, we've done that. Okay, that's just putting it into moles, identifying we're at the equivalence point, and realizing, hey, I made a bunch of weak base. I should do a weak base calculation like the ones I did in chapter 16. And we've done those many times. Okay? But it is, you've got a couple steps here. It is steppy. Okay? Questions on that process? Yeah. I skipped steps because I was running out of space, but what I did was I said, I'm going to take the negative log of that 1.5 times POH, and then I did 14 minus the POH to give me pH. Does that make sense? Yeah. You will see these problems on your Pearson homework and on your recitation. So if you're not like super comfy with it, don't worry, there's practice for you. But now we're going to do our last point on the titration curve. It's beyond the EP, all right? So now we're just dumping in excess OH minus. So this is also not too bad of a question. It's a BCA table followed by a strong base calculation. Okay? We're going to ask ourselves how much excess OH minus do we have, calculate a new concentration, and then calculate pH. All right? So we're going to try this now when we've added 60 mils. Again, we're starting with the same first step, calculate moles of HA and OH minus. When in doubt, start with a BCA table on titration questions. So moles of CH3COOH, they've not changed. That's still 0.125. Okay, our moles of OH minus are now 0.060 liters times 2.5 molar, and that was 0.15. So we'll put that in and we see, hey, our acetic acid, that's now our limiting reactant. I have excess OH minus. I've gone beyond my equivalence point. Okay, so I'm going to use that value and subtract it. And I gain that over here, but it's going to be, we get a little cheat here, which is nice. All right, so here is the end of after. Okay, here's what I have in my solution at this point. Okay, we do have a lot of our weak base. I've made 0.125 moles. That's more than my OH minus, but OH minus is a strong base, right? My weak base, my CH3COO minus, yes, I have more of it, but it generates a very small amount of OH minus. In fact, it's negligible. So if we go back to our last calculation, remember we said that we generated 1.52 times 10 to the negative fifth. So that's a small amount, okay? Well, actually, yeah, it was a small amount. I should put this into molarity, but it's small in comparison to what we have of our OH minus. All right, so let's convert this. All we have to do now is take this OH minus and bring it to molarity. Okay, so I have 0.025 moles of OH minus, and I'm going to divide it by 0.310 liters. That's my new total volume. I find that the concentration of OH minus is 0.0806, and that's really the number I should be comparing to our 1 times 10 to the negative fifth from the previous slide. If I add that in, sure, that number gets a little bit bigger, but it's negligible. It doesn't have an impact on the pH. So my pH is primarily dictated by the fact that I have all of this excess OH minus added in. Okay, so now I can take this and say my pH equals 14 plus the log of that number. And that is 12.91. Okay, so those are our 4 different regions on a weak acid, strong base titration curve. All right. Let's see. Questions on that before we move on? Okay. Let's chug. So I want to compare let's look at this graph. I'll explain it first. We're looking at weak acid versus a strong acid titration. So our y-axis is the pH. Our x-axis, we're adding in our mils of NaOH. And then the different colors show us different acids. All right, so this is a question that I think I have something of this flavor on my post-lecture where it says, hey, which one of these graphs is a weak acid, strong base titration? So how would you know that it was weak versus a strong acid in our original Erlenmeyer? So there's a couple things you want to point out. One, sort of obviously the starting pH is much lower for a strong acid. Right? So here's our strong acid in the black trace down here. So it's got a really low pH. If we start with a weaker acid, our initial pH is going to be higher because it's just not dissociating as much. Okay. The next thing, the pH at the equivalence point is greater than 7 for a weak acid. Okay, so the black dot there The black outline, that is our strong acid, and that's at a pH of 7. Everything else, so my red trace, my green, blue, and dark blue, those are weak acids, and the equivalence point pH is higher because that's where we've generated that concentration of weak base. So it should be a basic solution once we convert to the conjugate base. And the other thing that you can see in this graph is that the rapid rise for weak acids is smaller. So let's compare, like our strong acid goes, I'd say, it's like from here all the way up to here, okay? That's a really big change, whereas for our weakest of weak acids, this dark blue, it's from here to here, right? So it's getting smaller and smaller, okay, as our weak acid gets weaker. So you should be able to tell the difference or to look at a graph and say, I know that that's a weak acid strong base titration versus a strong acid strong base titration. Okay. All right. The last thing, I promised that we would be able to read some of this equilibrium information off of these graphs. All right, so that we can do that. The pKa, and we just make the statement, the pKa of a weak acid is the pH at the halfway point to the equivalence point. Why is that? So here's our equivalence point. It required 50 mils of NaOH. So what I'm saying in that statement is that the pKa of our weak acid, I'd look at half of 50, so that would be at 25 mils, and I'd say, what's the pH there? That looks like, well, I remember that this was acetic acid, so my pKa is 4.74. Why? Why that point? Okay? And we can read this quantitatively from the Henderson-Hasselbalch. Remember that the pH of a buffer, and we are in the buffer region of our titration curve, equals the pKa plus the log of A minus over HA. Okay? At this half point, okay, we have converted half of HA into A minus, which means that at that halfway point, the concentration of HA equals the concentration of A minus. Okay? At 50 mils, I have converted everything to A minus. Halfway there, I've converted half of HA. So those two are equal, which means I have the log of 1, which is 0. And pH equals pKa. So you can read the pKa of an acid off of this graph. Okay? Also a testy style question that we could ask you. Okay, look at this titration. What's the pKa of the acid? Okay, you look for the equivalence point, half that volume, what's the pH there? All right, let's quickly draw out what a curve would look for. I think this is what I want to do next. Yeah, a weak base, strong acid titration. So we're not going to do this. I think I assigned you a fairly long Pearson problem where you do what we just did, those 4 different steps, but you're going to do them for a weak base and strong acid. But let's predict what your graph is going to look like. Okay, so you'd have mils of HCl added, some strong acid, and you're going to track your pH. Okay, I'm going to start up here at 14 and mark our halfway 7 and then 0. All right, I know I'm going to start at a high pH. We have a base. Okay, I put a weak base in. I should have a pH elevated above 7. I start adding in acid. Okay, I'm going to be converting some of my base to BH+. So I'm going to start seeing a drop. And then all of a sudden, I'm going to see that rapid rise or rapid drop now. So in here, here's my weak base. So there's the weak base. Here's the buffer region where I have B and BH plus. And then this is my rapid rise. And I've drawn with care that my equivalence point pH is less than 7. Because now at this equivalence point, I have generated a solution of just BH plus, which is a weak acid. So I should have a pH less than 7. So I have just a BH plus, or weak acid, solution. That's why the pH has to be less than 7 here. Okay? And then beyond that, now we've added in more HCl than I had of my base, and so once I see how much HCl has been consumed, I take my extra and I calculate out my excess H plus. Okay? So the weak base, that's a weak base calculation. Here we would do a BCA table and then into a Henderson-Hasselbalch. Here I would do a BCA table and then into an ICE table. And that would be for the weak acid. Here I would do a BCA table and then into the concentration of H plus from the strong acid. And that would be my pH calculation. Okay? All right. Oh, I have one more point I want to make about, but I don't think I can get there. Okay. You guys, hold on. I have 3 minutes. I'm going to use them. Okay, you guys have an exam a week from tomorrow. All right? So after class today in the afternoon, I am going to release the practice exams. Okay, you will have the Pearson homework for follow-up questions. Tuesday is on the exam. What I lecture on Tuesday will be on the exam. If you want to do practice exams this weekend, I will post my lecture content for that from previous semesters. I wouldn't recommend using those practice exams until you know the content. Otherwise, you're just guessing. If you need anything else from me, let me know. Otherwise, have a great weekend, and I'll see you on Tuesday.